So the next problem is 1227. Probably I will first write it down and then 1227. So chapter 12, problem 27. And what do we have in this problem? DVD. You put it inside of your computer, right? And what does computer do? Of course, it will start accelerating it. First, of course, the disk is at rest, so then the computer starts accelerating it for some time, let's say for 3 seconds, in order to reach operating frequency, operating angular velocity, right? Only then, when the disk reaches operating angular velocity, let's say 2000 RPM, only then computer starts reading data. And of course, angular velocity of this disk doesn't change after that time. Okay, so let me write what is given, draw the picture, and whatever is useful and whatever is needed. So we have DVD. Right. Let me draw a small DVD. Right. Radius is given, let's say, a standard radius of a diameter of the disk, 12 centimeters. Of course, radius as a result 6 centimeters, or in meters it will be 0.06 meters. Then we have rotational motion of a rigid object. Of course, this is the axis of rotation. We're going to deal with this rotational motion, pure rotational motion. And of course, information about mass is not enough to describe rotational motion, as you remember. I keep telling you this. So we need a rotational equivalent of the mass. So moment of inertia. Moment of inertia is given. I think it's a 2.5 times 10 to the power of minus 5 kilograms times meters to the power of 2. Then, next, I will just plot. I think it's useful to plot angular velocity versus time in order to understand this problem deeper. Let me plot omega. Of course, that will be in radians per second, because the equations which we are going to use require these units, radians per second. And let me plot versus time. So we have a history of the motion of this disk. So first, disk is accelerated for 3 seconds. And we're going to assume that that angular acceleration is constant. Let me actually first write that down. So we'll make this assumption. Assume that alpha angular acceleration is constant. And actually it is true in the computer. So if the angular acceleration is constant, it means that angular velocity is going to increase at the constant rate, and we can represent it with a straight line. And then, okay, this moment of time is, let me label it T1, and it is given 3 seconds. So disk is being accelerated, is accelerated for 3 seconds. And once it reaches, disk reaches this angular velocity, let me label it omega 1, and give it. So this omega 1 is 2000 RPM. You remember, revolutions per minute. And then after this point, disk spins with constant angular velocity. Right? So it means that acceleration is 0. Right? So here, computer reads data. Over here, computer reads data. Right? So that is our operating frequency, which operating angular velocity. Operating angular velocity. Then, this angular acceleration, of course, that is the slope of this curve. Slope equals to alpha. And it is constant, right? It is constant, as I just told you. Then, what else? That is given, initial angular velocity is 0. So I can write that also down. Omega naught equals 0. The travel time, okay, let me write t1 equals 3 seconds. And I think that's what is given. So now, what do we have to find? We need to find torque that must be applied to provide this rotation and provide this angular acceleration. So what do we need to find? Let me write it here. So we need to find torque. That must be applied. So now, before we start discussing this problem, let me look at the picture where the torque is and something else. So first of all, what is the value of the torque over this stretch of time after t1 equals 3 seconds? Since now angular acceleration alpha is 0, you see, omega is constant. Omega is constant, it means angular acceleration is 0. So if angular acceleration is 0, remember rotational Newton's second law. Tau equals I alpha. If alpha is 0, torque is 0, right? Over here, since alpha is 0. Okay, so here torque is 0. So that's not what we want to find. Here torque is 0, we know that. Here, over this stretch of time from t equals 0 to t1 equals 3 seconds, since we have angular acceleration, non-zero angular acceleration, it means that torque is also not 0. So that's the torque which we need to find. Let me put it here. Torque. That's the torque. This torque. Okay, so now after this, I think we're ready to start discussing the solution. But before that, angular velocity is given in very useful units for our everyday life. Revolutions per minute or per second, that's what we use most of the time. But when you deal with physics, it's not the best even. It's not the best unit. So we need to, before we start solving problem, let's convert these angular velocity, these RPMs, into radians per second. Right? And then we will start discussing solution. So let's convert. Omega 1 equals 2000 RPM, revolutions per minute. Revolutions per minute. Okay, so I need to get rid of revolutions, I need to get rid of minutes. So I have to multiply this by ratios which are 1. First ratio, which is 1, right? I want to get rid of revolutions. Okay, it means that 1 revolution I will put downstairs in the denominator, and 1 revolution is 2 pi radians. So that is the first ratio of 1, which will help us to get rid of revolutions. Now we have to get rid of minutes. So to get rid of minutes, it means that 1 minute I will put upstairs, and 1 minute is 60 seconds. Again, that's another 1 ratio. This is 1. So, but this will help us to get rid of minutes. As a result, we have radians per second left. So if you multiply it all through, you will get 200 pi over 3 radians per second. That is pi. 200 times pi divided by 3 radians per second. So that's what we are going to use in our calculation. So now that's the introduction of the problem, and now let's start discussing what can be used to solve this problem. We need to find torque. Let's start from the end. And how many ways do we know to find this torque? To find torque in general. So first of all, we can use definition of the torque. Right? First, let me put first approach, a definition of the torque. And of course, I will use the absolute value. Absolute value we introduced in the previous lecture. Torque equals Rf. So R is a distance from the axis of rotation to the point where the force is applied, times sine of angle between them. In our problem, computer is a black box for me, right? I have no idea how much force is applied from that electrical motor on the disk DVD. At which point, is it at the center or at some distance from the center that force is applied, or those forces are applied? I don't know anything. And of course about the angle, I even know less than about these two guys. So pretty much we know nothing. Let me write. We know nothing. And I will put a depressing face. So this approach is not going to lead us anywhere. So let's think about the second approach. Second approach, where else have we seen torque so far in this class? In the rotational Newton's second law. This rotational Newton's second law, that universal law which is capable of describing a rotational motion of any classical mechanical system at any point of the universe, at any moment of time. But of course it must be classical mechanical system, right? Quantum mechanical system, that's a completely different story. So let me write it. Tau equals moment of inertia times alpha. Universal law. Okay, let me write. It's a rotational Newton second law. Next class, next lecture, we will introduce more general form of rotational Newton second law. But this law is general enough to solve this problem and tons of other problems. Right? But of course, next class we will introduce a more general form of the Newton second law. Okay, so let's start analyzing now this expression. Torque, that's what we need to find. Moment of inertia is given. So now the question, can we find the angular acceleration? Look, initial angular velocity is given. Final angular velocity is given over this stretch of time, final. And time is given. You can get acceleration even from this plot, from this graph. But I'm not going to use this graph. I'm going to use rotational kinematic equations, which we discussed a couple of months ago. But of course the question is, can we use them? Is it legitimate? And you see, we assumed that angular acceleration is constant. It means that our rotational kinematic equations can be used. Which equation? We have three of them. First for the angular velocity, second for the angle theta, and the third is the no time equation. In this case, time is given. Right, so it means that the third equation doesn't make sense to use. Of course, if you combine with something else, that can be used, but that's more efforts we would have to apply. Most likely we're going to use equation number 1 or equation number 2 for omega or for the angle. But since we have information about angular velocities at the initial moment of time, final, it means that equation number 1 will be, of course, the best. Right? Let me write something about this. So, since alpha is constant, we can use rotational kinematic equations. Right. And I'm going to use this one. Omega equals omega naught plus alpha times t. It's in general, right? In general, first rotational kinematic equations. Since I'm going to use this point as my final point because I have information about this point, so I'm going to use t1 as my final time. So I'll put here subscript 1, and as a result, my final angular velocity is omega 1. Then what else? Omega naught is 0. Omega naught is 0, so I can dump this term. And as a result, so we just need to, this is given, we need to find this in order to use it in the rotational Newton second law. So it's quite banal now. So alpha equals omega 1 over T1. Omega 1, we just converted into the units which we need in order to use our rotational Newton second law. In the rotational Newton second law, alpha must be in radians per square seconds. So omega 1, 200 pi divided by 3, of course that is in radians per second, and we need to divide by 3 seconds. So we will get 200 pi divided by 9. I still keep pi. It's not a crime, it's okay. 200 pi divided by 9 radians per square seconds. Okay, so now we have angular acceleration, right? So it's the slope of this curve. Of course, you could have used formulas how to find the slope of the curve, right? But it's basically exactly the same. So now we know this, so now we can go back to our rotational Newton second law and find torque finally. Right? So now back to our rotational Newton second law. I alpha, moment of inertia is given, 2.5 times 10 to the power of minus 5 kilograms times meter squared, n times alpha 200 pi divided by 9 radians per square seconds. Okay, if you multiply it, I'm going to look at my notes. You will get 1.75 times 10 to the power of minus 3. 1.75 times 10 to the power of minus 3 newtons times meters. Okay, so that's torque that the motor, electrical motor in the computer has to provide in order to, apply in order to provide this acceleration, constant angular acceleration 200 pi divided by 9. Okay, so that's this torque. Next, actually this is part A of this problem. Let me put over here. This is part A. Right. Now part B. Part B is reasonably simple. Now we need to find how many revolutions does this disk make over this period of time, from 0 to 3 seconds. So, of course, that can be easily found. It's basically a kinematic problem, right? About rotational kinematics. Again, let's recall our equations. First equation for omega, of course, we don't need it. A second equation to find angle, of course, that's what we need because we have time. Because time is given. So now let me write what do we need to find? Theta 1, number of revolutions. Now we need to find number of revolutions between t equals 0 and t1 equals 3 seconds. Okay, so the rotational kinematic equation, theta equals theta naught plus omega naught t plus 1 over 2 alpha t squared. This is alpha, that is 2. So now let's simplify because it can be easily done. Every time we can make omega naught 0, it's not a big deal. So omega naught is 0. Theta naught is 0. Now omega naught is 0 because disk starts spinning from rest. And so what's left? 1 over 2 alpha t squared. Alpha is here. Time is given. So we just need to multiply it through to get the final number of revolutions. 1 over 2 alpha 200 pi over 9 radians per square seconds times 3 seconds to the power of 2. 2 seconds here, 2 seconds there can be cancelled, so we will have only radians, which that's what we are supposed to get. Then 3 to the power of 2 is 9, and we have 9 here, so that will be cancelled. And we have 2 here and 2 there. Also, those 2 will be cancelled, and we will have only 100 pi left. So 100 pi radians. So that's the angle. But again, radians are very useful when you do physics, when you do these calculations, but in everyday life, radians are quite awkward to use. So of course, let's convert it back to our RPM, revolutions per minute, because again, in everyday life, that is of course the most convenient. So, yeah, I should have put subscript 1. So now theta 1 equals 100 pi, and that is in radians. And now I need to multiply by the ratio, which is 1. And since I want to get rid of radians, so radians must be downstairs. So we'll use 2 pi radians. That's 1 revolution. 1 revolution. 100 pi divided by 2 pi, that's why I was dragging pi throughout the whole solution. So we will get, of course, just 50 revolutions. 50 revolutions. So that's the answer for part B, number of revolutions over this stretch of time, 50. And for part A, torque, which the motor applies to provide this acceleration, is 1.75 times 10 to the power of minus 3. So that's the problem 1227. And that's it. Good luck with your homework.